Okay, so hello everyone. I welcome you all to the first student talk of chemistry by Science Activities Club NISER of this session, and a warm, heartfelt welcome to the fresh minds of batch 2020. This is Suritro, a fourth year student of chemical sciences, and I guess this is the first among all the non-academic beyond the course events that you guys are attending, the batch 20 students. And we feel really bad that we still haven't normalized ourselves with the new normal yet. Also, 400 of us are still in our quarantine. And I hope amidst the pressure and packed schedule we all have, the talk will refresh our minds. So, without further ado, let me quickly introduce you to our today's speaker, Adya Anwesa Mahapatra, a third year integrated MSc student from School of Chemical Sciences. Adya has been fond of elements of biology since her school days and is drawn towards the understanding of their chemistry. She aspires to use her knowledge in biological applications and interdisciplinary research works. Adya also says she is quote unquote a bit curious and considers Google as her go to place for anything and everything that happens under the sun. And it is her very thirst to explore that drives her to science, to understand what doesn't meet the eye. She finds life under microscope very pretty. And beyond the lab, Adya is an amazing artist, a foodie, and my personal favorite relatable meme dealer. So that was the least I could have said about her. Let's get to listen to what she has to say about artificial photosynthesis.
Hello everyone, this is Adya, and today I'll be talking about artificial photosynthesis systems for high efficiency pure water splitting. This presentation is based on my summer work. I was asked to study and review all the developments in artificial photosynthesis in the last 5 years, so this talk is mainly about my review on the topic. In today's presentation, I'll first tell you what artificial photosynthesis is and what device we are trying to build in labs. I'll also walk you through a few specifications the device needs to have, how to improve the efficiency of the system, and finally, I'll discuss a few artificial photosynthesis systems currently in use. So let's start. Before I tell you what artificial photosynthesis is and what water splitting is, let me tell you the why behind it. As in, why even pursue these ideas? So, statistically speaking, this decade is witnessing the widest consequences of man made activities on our planet. We are facing global warming, climate change, and pertinent health risks. The air and water pollution levels due to toxic gases, chemicals, ultrafine particles from industries, agriculture, and transportation sectors are beginning to take a toll on our health. In fact, everyone is at risk of inflammatory diseases and lung infections to cancer and death. Along with that, our planet is also slowly dying. Changes observed in Earth's climate change since the early 20th century are primarily driven by human activities, particularly fossil fuel burning, which increases heat trapping greenhouse gas levels in the atmosphere, raising the average surface temperature. Now, this has a broad range of observed negative effects, as we are all aware of. The origin of this strong imbalance between human activities and environment can be found in the massive exploitation of resources, that is, endless use of cheap energy sources like coal, petroleum, and fossil fuels. Now, these are commonly known as non renewable energy sources and they release carbon dioxide, methane, and other greenhouse gases into the atmosphere. They are called greenhouse gases because they have an overall warming effect on the planet. And as we consume more non renewable fuel, we continue heating the planet, which contributes to change in weather patterns. That in turn affects the food production, animal ecosystem, and essential biodiversity loss. The damage done is now too large to ignore. We need to do something and we need to do it soon. Since things are not going to change on their own, we will have to make a conscious effort to move on to new strategies to reduce our ecological footprint and also the environmental and health impact. And we need to make this transition within a decade to avoid the devastating environmental hazards, resource depletion, and world economic crisis. Now, the new energy source that we need to move on to should be first of all clean, renewable, and sustainable, obviously. But along with that, since we cannot directly use renewable energy, they have to be first made available in easily consumable way for their large scale implementation, for which its fabrication and refinement should be cost effective, possible at normal temperature levels, and its generation should be based on highly efficient materials that mostly contain earth abundant elements, that is, the elements abundantly available on Earth's crust, and they should be easily extractable and fully recyclable. Now, the major renewable energy sources include solar, hydraulic, geothermal, tidal, and wind energy. Out of all these, my interest lies in solar energy and using it to replace the other non renewable energy sources efficiently. Let me tell you why exactly do I prefer solar energy. Among renewable and exploitable energy sources, nuclear fusion energy or solar energy is by far the largest. You might not know this, but the sun provides more energy to our planet per hour than the total energy consumed by human activities in 1 year. So, the conversion of solar energy to fuel seems as an effective solution to combat this growing energy demand in a sustainable way. Now, if solar energy is to be a major primary energy source, then it must be stored and dispatched on demand to the masses. So, the question is how to store solar energy? An attractive approach to store solar energy is in the form of chemical bonds as occurs in natural photosynthesis. Plants have been using this solar energy to fuel themselves since the beginning of time. Natural photosynthesis, which is conducted by cyanobacteria, algae, and plants, uses solar energy to reduce carbon dioxide to carbohydrates. I think it's now fairly clear as to why we need to switch to solar energy and how exactly are scientists planning to store it for everyday consumption. Now, for efficient photosynthesis, plants have evolved into highly organized photosynthetic systems. This includes interconnected light harvesting systems, efficient charge separation units, reaction centers for photosystems 1 and 2, electron transport chains, redox carriers, and CO2 reduction units. I will tell you a bit about the underlying mechanism of natural photosynthesis before moving on to the artificial process that we are trying to design. The light-driven water-splitting reaction occurs in pH2 of plants, algae, and cyanobacteria. Solar energy is absorbed by chlorophyll and other pigments and is transferred efficiently to pH2 reaction center where the charge separation takes place. This initial conversion of light energy to electrochemical energy is generated by a radical pair state P680 plus and pheophytin minus. P680 is a chlorophyll molecule and pheophytin is another biochemical molecule. The redox potential of P680 plus is highly oxidizing. It is estimated to be about 1.2 volts, while that of pheophytin is about minus 0.5 volts. We know that the standard reduction potential for hydrogen is fixed at 0, and as per the electrochemical series, any species with a more negative reduction potential can act as a reducing agent and reduce another species with less negative reduction potential. So, as I said, pheophytin has a reduction potential of minus 0.5 volt, and that of hydrogen is fixed at 0. Therefore, pheophytin is sufficiently negative that in principle it could drive the reduction of hydrogen H plus into hydrogen gas. The reducing equivalent then produced is passed along an electron transport chain to PS1, where it is excited by the energy of a second photon absorbed by a chlorophyll molecule known as P700. This lifts the reducing potential to minus 1 volt. In this way, sufficient energy is accumulated to drive the fixation of CO2. The P680 plus species generated in PS2 drives the splitting of water at the water oxidizing center. The splitting of water into dioxygen and reducing equivalent is a 4 electron process, and therefore PS2 must absorb 4 photons to drive this half reaction for the subsequent reaction. Now, the water splitting reaction of PS2 holds the greatest promise for the development of new technology for converting solar radiation into usable energy, particularly in generating hydrogen equivalents for reducing carbon dioxide. The redox reaction that is involved in the water splitting that I've mentioned for you in the slide here below is oxidation half. Water is oxidized into oxygen and releases 4 electrons in the process, and in the reduction half 4H plus is reduced to hydrogen molecule with the help of 4 electrons. Now that we know a little bit about natural photosynthesis reaction, let us talk about artificial photosynthesis. Artificial photosynthesis aims at mimicking the natural process using man-made devices and is thought of as the best way to convert and store solar energy into chemical fuel. It aims at converting abundant materials in nature like seawater and carbon dioxide to useful chemicals like hydrogen and other hydrocarbons. Artificial photosynthesis primarily involves a photon absorbing center, a catalytic center with an electron and hole transfer pathway that joins the two. The photon absorbing center is usually a semiconductor which absorbs light and generates an electron and hole pair. The electron is used in reducing water while the hole drives the oxidation process. As we saw in the last slide, electrons helped in reduction process and in oxidation process the electrons were released. Now, artificial photosynthesis can proceed by two steps. One is a single step process and the other is a two-step process. Let me explain you the diagrams here. In the single step process, we have one semiconductor. In one half, the water is getting oxidized to O2 and four electrons are released. The four electrons are now stored in the valence band of the semiconductor. When enough light falls on the semiconductor, the electrons gain enough energy to transfer from the valence band to the conduction band. There, the electrons now reduce the H plus into hydrogen. Two-step process essentially is the same, but here oxidation half and reduction half take place in two different semiconductors. In one semiconductor, the water is first oxidized to O2 and electrons are released. Those electrons move to the conduction band and then there is a redox relay, which means here we have iron or iodine or any other molecules that will take up the electrons to get reduced themselves. That molecule is now attached to the second semiconductor here. When electrons are passed from that molecule to the semiconductor, it is stored in the valence band, and when light falls on it, the electrons then move from the valence band to the conduction band, and there again the hydrogen gets reduced to H2. Now that we know the basics of artificial photosynthesis, let us talk about different approaches towards building an artificial photosynthesis unit. Out of the many known methods, I would like to tell you about two proposals. One is with carbon compound production and the other is through water splitting approach. We will start with artificial photosynthesis with carbon compound production. This is also known as photocatalytic conversion of CO2 to hydrocarbon fuel. The approach is to simultaneously reduce CO2 with the formation of hydrogen. As we can see in the equations given here, in the oxidizing half, water gets oxidized into oxygen, and in the reduction half, H plus gets reduced to hydrogen. But we have also added a CO2 molecule into the reduction half if you notice here. This CO2 also gets reduced to hydrocarbons. So in this process of artificial photosynthesis, we have the added benefit of CO2 reduction along with the hydrogen generation as originally thought of. The photocatalytic reduction of carbon dioxide is similar to the process of photosynthesis for green plants. The photocatalysts play the role of green plants to convert CO2 into fuel using ultraviolet or visible light. Typically, this reaction can be divided into four steps. First, the catalyst is activated by UV or visible light from sunlight or any other illuminated light source. Subsequently, the electrons in the valence band leap into the conduction band. Simultaneously, holes are left in the valence band. This forms a negative electron and positive hole pair, which respectively act as the reductants and oxidants for reducing and oxidizing the substances. That is, the electrons act as reductants and carry out the reduction process, whereas holes will act as oxidant and help in the oxidation process. Thirdly, the generated electron hole pairs separate and transfer to the surface of the catalyst. And in the fourth step, the reduction of CO2 takes place in the surface by the negative electron, and that generates corresponding products such as CH4, CH3OH, carbon monoxide, and other such hydrocarbons. The problem with this mode of artificial photosynthesis is that it is fundamentally a challenging process, as carbon dioxide reduction to carbon dioxide minus anion or carbon monoxide requires a very high activation energy. New electrocatalysts are being developed to reduce the activation energy of carbon dioxide reduction. We have an example. Partially oxidized atomic cobalt layers show a good result. However, efficient production of hydrocarbon remains a very difficult challenge till now due to the inefficient carbon dioxide reduction approach. Now, let's move on to the second part, artificial photosynthesis with water splitting approach. Water splitting is a more favorable and competitive process than carbon dioxide reduction as the overall carbon dioxide reduction for most systems are limited. Large-scale reduction of atmospheric carbon dioxide is an issue compared to hydrogen production because one is the high activation energy required for CO2 reduction and the other is that CO2 concentration is relatively low in the atmosphere. Thus, now it's fairly obvious to say that the best feedstock for synthetic, renewable, and clean fuel is the most freely available resource on Earth, that is seawater. Hence, hydrogen generation from water using photosynthesis approach seems as the ideal scenario and is the key for a clean and sustainable future. Now, converting light energy to chemical bond energy while splitting water requires three main steps, which are light absorption, charge carrier transportation or separation, and surface reaction. First is light absorption. Here, oscillating electric field of the incoming light induces an oscillating dipole within the molecule associated with the photosynthetic system, leading to electron transition to a higher electronic energy state. Next, we have charge carrier transportation. Here, photoexcited electrons and holes separate at the interface, the energy being carried by the electrons and holes. And finally, we have surface reactions. At the surface of the material, the electrons and holes reduce and oxidize water to produce hydrogen and oxygen respectively, with the energy being stored in chemical bonds. All the three steps should be efficient enough to achieve substantial overall conversion efficiencies. However, till date, there is no single material that meets simultaneously all of the requirements. Some are better at light absorption, while others are at charge separation. But no material yet meets required band gap, band edge position, electronic property, and long-term stability. One of the major challenges lies in finding a long-lasting, robust water oxidation catalyst. Though no material efficiently meets our expectations, there is one honorable mention. Back in 2001, a semiconductor junction device consisting of aluminium gallium arsenide or aluminium gallium silicate was reported, which was capable of splitting water at a record efficiency of 18.3%. But unfortunately, the material device was unstable in aqueous solution, which prevented its application for practical solar water splitting purposes. Okay, so I think you know what we'll be majorly focusing on artificial photosynthesis via water splitting approach and not the CO2 reduction method. Let us talk about how we can model a device that will essentially carry out this process. With the advent of science and technology now, material structures can be precisely modified to achieve enhanced electronic and surface properties. A few new strategies that are recently being used to fine-tune the materials and also to improve the overall efficiency of the process are nanostructural design, heterojunctions, surface passivation, surface engineering, and surface reactions. Now we are going to discuss each of them one by one. First, we have nanostructural design. See, a charge recombination still remains a major barrier for efficient photoelectrochemical water splitting. Charge recombination means when generated electrons lose energy and combine with the hole again. That defeats the whole process because we know electrons are needed for oxidation of water. This means the competition between charge separation and recombination will determine the overall efficiency of this reaction. For materials with poor charge mobility, nanostructuring can be done. Nanostructuring is the designing of nanoscale structures of required dimensions, and it is a successful strategy to overcome this problem. Smart nanostructures with ordered designs improve the surface area and prevent chargeback recombination. As we can see, plants have evolved unique structures that efficiently handle complex photosynthetic processes such as light harvesting and charge collection. This was difficult to obtain in lab earlier, but now with easily accessible and low-cost nanostructure synthetic procedures, fabrication of such complex structures is relatively easy. For example, a tree-like structure that you can see in the diagram here with stems and branches was constructed using conductive aluminium doped zinc oxide which was then used as an efficient electron collector. This tree-like structure helped in enhanced light trapping, larger surface area, and better electron-hole separation. Many other such structures have been reported in scientific articles. They are made out of mainly earth-abundant oxides such as titanium dioxide, tungsten trioxide, and ferric oxide. The next one is heterojunction. Along with nanostructuring, we have also been looking for other charge separation enhancing structures such as heterojunction. A heterojunction is an interface that occurs between two layers or regions of dissimilar semiconductors. These semiconducting materials have unequal band gaps. The energy difference between the conduction band and Fermi level can be achieved by adjusting the doping level. Hence, a preferred energy match between the two materials can be achieved with a built-in voltage established by electron flowing from one side to the other until Fermi levels on both sides equalize. Another efficient way to reduce recombinations consists of depositing an ultra-thin layer onto a nanostructure. That will increase the photon absorption and also decrease the distance that the charge carrier has to travel before reaching the surface. For examples, photocurrents as high as 3 milliampere per centimeter cube at 1.23 volt was achieved on an ultra-thin hematite film deposited on a 3D nanophotonic structure. Advances over the past few years have demonstrated great improvements in efficiency through nanostructuring and heterostructure designing. As a result, the typical photocurrent density for this material has now increased to a value of 3 to 5 milliampere per centimeter square. Since we were talking about band gaps while discussing heterojunctions, it is worth mentioning that narrow bandgap semiconductors have been seen to effectively show water splitting. This is because narrower the band gap, easier it is for the electron to jump from valence band to the conduction band. Semiconductors with appropriately narrow band gaps and band levels are especially good for water oxidation and reduction. In this context, oxynitrides and nitride composites are slowly gaining popularity. Metal-free nitrides like C3N4 has narrow band gap of only 2.7 electron volt, and its conduction band is sufficiently negative to drive photon reduction to hydrogen with stability. Now, silicon semiconductors are emerging for water splitting because they have optimum band gaps, they also have long carrier lifetime, and they have great charge carrier mobility and proper bandage positions. Now, the new challenge is to protect these silicon semiconductors against corrosion in aqueous solution. That makes us wonder if only there was a way to protect these otherwise perfect semiconductors. If only we could find a way that would ensure their stability under electrolyte, and then they could be very efficiently used for water splitting. So, luckily for us, there exists a way. It is called surface passivation. Let me tell you about it. Since narrow bandgap semiconductors face stability issues, a protection layer is employed on top of it to enhance their stability in aqueous medium. As passivation layers can readily be deposited onto high surface area by diverse fabrication techniques, of course, they are being adopted as a simple yet very efficient way to facilitate the use of well-known aqueous unstable semiconductors. In addition to protecting the semiconductors from corrosion, surface passivation layers also prevent surface electron hole recombination, and this helps in further enhancing the activity of semiconductor. The most effective material so far for passivation is titanium oxide. This has been tested on silicon, gallium arsenide, and indium phosphide. Other materials like ultra-thin carbon sheath was deposited on dicopper oxide based heterojunctions as a surface protection layer. It protected the semiconductor against photocorrosion and helped improve performance in photocurrent density and potential. Other examples include dual layer thin titanium oxide or nickel coating, which can be used to stabilize crystalline bismuth banded photoanodes against corrosion in aqueous alkaline electrolyte of pH 13. Strontium titanate can also be used as a protection layer for silicon photocathodes. It prevents corrosion without compromising photocatalytic redox activity. Here I have a table that summarizes the most common surface passivation agents with their performance and stability specifications. As you can see, on one hand we have semiconductors, then we have their specifications, next we have the conditions under which they can be applied, then we have performance and stability chart. Now moving on, After talking about surface passivation, now let us discuss about other surface engineering techniques that will help in increasing the overall efficiency of water splitting. Earlier, it was believed that water oxidation took place mainly from valence band holes with the help of charge transfer process at electrolyte interface. But now, various studies have suggested that water oxidation actually takes place mainly from surface trapped holes and not the deeply lying valence band holes. So now we can modify the semiconductor such that water splitting is more favorable at the surface of the semiconductor. For instance, it was found that hydrogen doping eliminates the recombination centers at the surface and inhibits the recombination of electrons and holes. That can be used. Also, titanium dioxide coating on p-type gallium indium phosphides was also found to be effective at suppressing this reverse process of unproductive recombination by an enhanced charge separation of the excited electrons and holes. It is also notable that interfaces other than the surface between active layer and electrolyte can also be modified for enhancing charge separation and transportation. For instance, in fluorine tin oxide, the underlayer works as barrier layers. The so-called barrier layer stops the electron migration from conducting layer to the active layer. So the same underlayers were then used to prevent the recombination of electrons with holes in the valence band of the active layer, leading to a better charge separation in fluorine tin oxide. It was also reported that tin oxide nanoparticles in presence of tin shifted the top of the valence band upwards, and that narrowed the band gap. It also promoted better charge carrier separation. A maximum efficiency of 62% has been achieved using these surface engineering techniques. Now, we are at the final part of modification techniques for water splitting approach. This technique is called as surface reactions. See, so far we have noticed that one of the major obstacles for achieving efficient, stable overall water splitting is directly related to the uncontrolled surface charge properties. Water splitting takes place on the surface of the semiconductor, but often the surface is also the site for charge back recombination and corrosion. Here comes the role of a co-catalyst. So first of all, what is a co-catalyst? A co-catalyst is a chemical species that acts with other catalysts to enhance the overall catalytic property of a reaction. Loading metal co-catalysts is the most popular way to increase the activity of the semiconductor. Loading a co-catalyst onto a semiconductor can lower its voltage and also the activation energy for hydrogen production. It can also capture the electrons to suppress electron-hole recombination, and the co-catalyst can also act as reaction site for reduction of H+. Transition metals and their oxides have been employed as co-catalysts to enhance the rate of reduction of H+. The table given here summarizes the performance of recently reported OER and HER catalysts. OER is oxygen evolution reaction and HER is hydrogen evolution reaction. Now we can know from the name itself that oxygen evolution reaction is the process of generating molecular oxygen through chemical oxidation of water. This reaction proceeds through multi-step proton-coupled electron transfer, which are kinetically slow reactions. The details about it I'll explain in the next slide. So, in most metal oxides, the localized oxygen nature of valence band contributes to a low mobility of holes and thus inefficient hole transfer. This means because of the large electronegativity of oxygen, the valence band edge of oxides is strongly localized on oxygen ions. Then the positive holes introduced at the edge are also localized on oxygen ions, and now that constitutes for a deep trap. The positive holes cannot migrate within the crystal even under an applied electric field. So here also we need to take the help of co-catalyst, which will help decrease the activation energy. Without such catalyst, the holes reaching the surface may not accept electrons from water, but instead they will recombine with electrons in the conduction band of the semiconductor. Traditional effective oxygen evolution reaction catalysts are typically iridium oxide and ruthenium oxide, but they cannot be implemented on large scale due to their limited availability in nature and they have very high cost. Earth-abundant co-catalysts have received great attention now. For example, cobalt-based thin films are showing enhanced catalytic reaction in the presence of inorganic phosphate and borate. Cobalt phosphate co-catalysts were found to facilitate the water oxidation reaction by suppressing surface recombination materials such as ferric oxide, bismuth vanadate, and others. Nickel ion layered double oxides is also an efficient co-catalyst for water oxidation on tantalum nitride. Now, with the growing number of co-catalysts being reported, the next big thing to do is to further improve their activities. In the last slide, we talked about oxygen evolution reaction. Now let us talk about hydrogen evolution reaction. For hydrogen evolution reaction, noble metals such as platinum and rhodium are excellent promoters for hydrogen evolution. They have one drawback though. They also catalyze the undesired back reaction, which limits the solar to hydrogen efficiency in artificial photosynthesis. To avoid such a drawback reaction, transition metal oxides such as nickel oxide and ruthenium oxide are usually used as co-catalysts for overall water splitting. They do not show the undesirable back reaction of water formation again from hydrogen and oxygen. Recently, an oxidized platinum cluster was also reported as an efficient hydrogen evolution reaction catalyst, and it also checked the undesirable hydrogen back oxidation. Nickel oxide, or even simply nickel, on carbon nanotube sidewalls also acts as a highly effective hydrogen evolution reaction electrocatalyst. It shows activity similar to that of platinum. But as platinum is a precious metal, new non precious metal electrocatalysts are being tested for hydrogen evolution. For example, molybdenum disulfide has been studied as an electrocatalyst for hydrogen evolution reaction, and it showed high performance. The hydrogen production rate was improved by 28 times after loading molybdenum sulfide onto sodium tantalum trioxide. Other new compounds such as molybdenum carbides are also showing excellent electrocatalytic performance for hydrogen production. It has also been found that metal-free co-catalysts such as carbon dots are capable of cost effectiveness but also still underperformed as compared to platinum. Okay, so that marks the end of techniques that can be used to enhance water splitting process. Now let us move on to the final part of my presentation. Here I'll tell you about a few water splitting systems that are practically in use now. I will talk about Z-scheme, natural artificial hybrid system, nanoparticle system, dye-sensitized cells, and electrolysis. Of course, this list is not exhaustive and there are many more systems in use, but we will focus on these five systems for today's presentation. Let us start with the first one, that is Z-scheme. Z-scheme is a system that consists of two narrow bandgap semiconductors for photooxidation and photoreduction, and they have an electron mediator. The Z-schematic water splitting has been reported as a promising approach to overcome the limitation of charge carrier recombination and back reaction of products by isolating electrons and holes. Here what we are doing is performing the oxidation and reduction in two separate chambers. That should stop reaction of hydrogen and oxygen combining again to form water again. Remember the two-step artificial photosynthesis process I discussed earlier? Here we will be using that. Suitable redox couples such as iodate and iodide ion or ferric and ferrous ion are commonly used as electron mediators. Photocatalysts that are active for hydrogen and oxygen evolution can be used to construct the Z scheme. Z schematic water splitting proceeds accompanied by electron transfer from an oxygen evolving catalyst here in this part of this Z scheme to the hydrogen evolving photocatalyst there in this other part of the catalyst. So the ionic electron mediators efficiently transfer electrons by adsorbing onto the surface of these catalysts. The limitation of this method are that usable catalysts are limited because suitable adsorbing and desorption properties of electron mediators on catalysts are required, and back reaction by ionic electron mediators may proceed. For example, when a metal sulfide photocatalyst is combined with an iron ion electron mediator, the iron ions are deposited on the surface of the metal sulfide as iron sulfide. Now, this is something we don't want to happen. Recently, a solid state electron mediator was used to replace the redox couple in this system. A P-type metal sulfide photocatalyst was used as the hydrogen evolving catalyst and was combined with titanium oxide as the oxygen evolving photocatalyst. And reduced graphene oxide was used as the electron mediator between the two to split water into hydrogen and oxygen. Systems with other solid electron mediators such as silver or gold or even without an electron mediators are also reported. Here as no redox couples were used, the stability as well as charge transfer were simultaneously improved. So that's all I had to say about Z scheme. Next, we have natural artificial hybrid systems. Out of the oxidation and reduction process taking place during artificial photosynthesis, oxidation of water into oxygen is a difficult process. Out of the many discovered photocatalysts discovered for oxygen evolution reaction, there is no one impressively efficient enough. Whereas the hydrogen evolution reaction, there is the reduction of H plus into hydrogen that is relatively simple. As we all know, PS2, which is naturally occurring in plants, is an excellent water oxidizing center. So, keeping that in mind, scientists have thought of a hybrid system where they will be integrating the naturally occurring PS2 with the artificial photocatalytic material. So, a natural artificial hybrid system, also known as a photobiocatalyst, is a system combining a semiconductor as the light harvester and an enzyme activated by the semiconductor. The most widely studied photobiocatalyst system so far makes use of conduction band electrons of excited semiconductors to promote enzymatic reductions in PS2. In early stage, the research on PS2 modified electrodes were made for the solar to chemical conversion. For electron transfer between PS2 and electrodes, the redox polymers like polymercapto P-benzoquinone, polylysine benzoquinone, and polybenzoyl violazine were widely used. Although continuous progress has been made during the past years, the efficiency is still low for natural artificial photosynthesis hybrid systems. This could be because of the poor electron transfer from PS2 to artificial components due to some complicated reason such as slow kinetics, the undesirable contact of PS2 with a catalyst, or maybe because of unmatched potential. Thus, to deal with these issues, offering a strategy to bridge PS2 and the artificial parts of efficient electron transfer is of great importance. A natural artificial hybrid Z-scheme system was reported that integrated plant PS2 and inorganic photocatalysts ruthenium or strontium titanate coupled with ferro and ferricyanide as an inorganic electron shuttle. Very recently, a hybrid approach combining inorganic semiconductors with nanophotosynthetic bacterium was reported. Here, cadmium sulfide nanoparticles were attached to the bacteria. The cadmium sulfide served as the light harvester, enabling continuous photosynthesis of acetic acid from carbon dioxide. Next, we have nanoparticle systems for overall water splitting. For photocatalysis based on nanoparticle systems, a sacrificial agent is used as a whole scavenger to protect the photocatalyst from self oxidation. Overall water splitting without any sacrificial agent is therefore of particular interest due to its simplicity and potential low cost of operation. One successful example is the cobalt oxide photocatalyst capable of splitting pure water into oxygen and hydrogen under visible light. Cobalt oxide nanoparticles showed an overall water splitting efficiency of around 5%. This particle system can also be regarded as a wireless version of photoelectrochemical cell. The co-catalyst representing the counter electrode is placed on the surface of the co-catalyst representing the working electrode. This system showed unexpectedly good stability in aqueous solution. Surface modification was also used to prevent back reaction in this compact system. A metal-free photocatalytic system for harvesting photons for photosynthesis has also been reported. In this system, charge carrier involved in both the oxidation and reduction steps come from the excitation of a gold nanorod. The total efficiency was low of only 0.1%, but the operational lifetime of the device was relatively long. But since the efficiency was so low, this was not further pursued. Then we have dye-sensitized photoelectrochemical cell. In this system, water oxidizing catalysts are coupled to the dye molecule to serve as electron donors to regenerate the oxidized dye molecule. Water molecules are oxidized to oxygen and a proton by the water oxidizing catalyst, while the protons are reduced to hydrogen at the counter electrode. Dye-sensitized cells consist of wide bandgap nanoparticle, metal oxide semiconductor, and catalyst assemblies, aiming to drive the two half reactions of water splitting at physically separated two compartments. Dyes act as the light trapping agents, and catalysts are used for hydrogen production and oxygen production. The charge transfer between the dye and the catalyst plays an important role. This can be better understood with the help of an example. Let's say a dye-sensitized photoelectrochemical cell is composed of a dye, a water oxidizing catalyst, and a titanium oxide attached to the electrode surface. Now, if you look at this diagram, here water is getting oxidized to oxygen, and in the process 4 electrons are removed. Those electrons are now in the surface of water oxidizing catalyst. They can lose some energy and move on to the valence band of the dye 1 since it is at a lower energy state. Now when light is illuminated upon this semiconductor, the electrons will move from the valence band to the conduction band here. After relaxation, the electrons will jump to a lower energy state that is available in the titanium oxide. So now that since the electrons are on the surface of titanium oxide, this will help in the conduction of electrode from this end of the photochemical cell to the other end. Now, when the electrons are here, they can lose some energy and they will then jump to a lower energy state that is available with dye 2 valence band. Now when sunlight is illuminated on this surface, the electrons will jump from the valence band to the conduction band here, and after further relaxation they can jump back to this surface which is of a hydrogen evolving catalysts. And when the electrons are on this hydrogen evolution catalyst, they will help in the reduction of H plus into hydrogen evolving H2. The dye-sensitized cells have only one disadvantage though. They show low overall solar energy conversion efficiency as well as poor long-term stability. A practical dye-sensitized solar fuel production requires long-term aqueous photocathode stability. New sensitizers were used to prevent both dye desorption and semiconductor degradation to achieve excellent stability. The final water splitting system I will be discussing is the normal electrolysis system. A recent trend for affordable solar water splitting is electrolysis, which is an artificial photosynthesis system combining a cell with a standard water electrolyzer for efficient production of hydrogen. In this system, water is decomposed into hydrogen and oxygen by the electric current produced between the electrodes of the connected cell. Commercial water electrolysis is typically operated at high current densities of 1 to 10 ampere per centimeter square. Such high current densities require a higher operating voltage. In such operating condition, the electrolyte conductivity is an important factor. Recent electrolysis systems give a remarkable electrical to chemical energy efficiency of 83.3%. Now, earth abundant elements have emerged as very promising candidates for this. It is because of their high efficiency, low cost, and low manufacturing costs. Electrodes made out of these elements were connected to a solar cell. This yielded a water splitting photocurrent density of about 10 milliampere per centimeter square and an overall solar to hydrogen efficiency of 12.3%. One of the major demerits of this system is its stability. So that was all about artificial photosynthesis and the various devices used to achieve it. As though it may seem much, but from a scientific point of view, a lot still remains to be done. Honestly, artificial photosynthesis as a concept is still in its baby stage. The first thing that needs to be done is understanding the water splitting and electron separation techniques in natural photosynthesis. Plants over time have evolved into these complex photosystems that effortlessly carry out the entire process. In order to be able to fully replicate it, we will have to look at these photosystems with more scrutiny. A complete understanding of the rate determining steps would provide more insight into structure, composition, reaction rate relations that can be used to improve the overall rate of the reaction. Aiming at the significant improvement of water splitting efficiency, attention should be focused for better fundamental knowledge of the photoelectrodes that we are using. Though the advantages of material and structural engineering for increasing efficiency are now confirmed, their microscopic origins are still not properly understood, and there is also a great need for efficiency standardization. So, in conclusion, without a doubt, using the two most abundant free renewable sources on our planet, that is the sun and water, to make unlimited amount of clean hydrogen, also oxygen, is the way forward. Indeed, it will provide a clean and sustainable energy resource while releasing water as the only emission product of burning this fuel. This definitely makes sense, and that's why scientists are now actively pursuing the process of artificial photosynthesis. That was all I had to say today. Here I have listed all the sources that I took help from. You can visit them in case you want to learn more about the topic. And if you want to discuss artificial photosynthesis with me, you can find me here. That's my email ID. Thank you for your time.
Thank you so much, Adya. That was indeed very informative and talked about something interesting. In case anyone has any question, I would request you all to use the raise hand feature. We can address the questions one by one. Yes, Uday, you can unmute yourself and ask the question.
Like in the natural systems, the efficiency is very low, right? Even in the plants, the total efficiency is very low, I think. So how can we use that to model something? Because already the efficiency is pretty low.
In plants, the efficiency is low, but if you see the total statistics, plants use only 0.03% of the total solar energy that sun provides to produce oxygen throughout the day and night. So, if we can replicate that in the lab, that will be a great achievement. We can take limited quantities of water and then that we will use to convert it into hydrogen as a fuel.
Like the solar panels have efficiency, I think around 20 or something reaching 50%. So we have a better system to transfer, like to make electricity. So is there any advantage of this like water splitting?
Yes, that was what I mentioned first in the slide. We are not only doing this for the generation of electricity, we are also trying to replace this coal, petroleum, and everything else and use hydrogen instead of that. So, the main purpose here is not to generate electricity, it is to generate hydrogen as a fuel.
Thank you.
Anyone else has any question or would like to ask something in general can raise the hand. Okay, if anyone else doesn't have any question, we can end today's session here. Uh, okay, Tanya appreciates how good the presentation
Thank you.
was.
Thank you so much.
Okay, so in case anyone doesn't have any further questions, we can end today's session here. And the new students, it's for the new students. If you have any questions regarding the events or the student talks, and if you also want to be a part of the student talk, you can directly mail the to Science Activities Club. Okay, Praveen Bawali, you can unmute yourself and ask the question if you have.
Can we increase the oxygen by artificial photosynthesis?
Yes, obviously, photosynthesis as the process is conversion of water into oxygen. So, obviously, oxygen will be released as a byproduct. That I also mentioned several times. Here, our focus is on producing hydrogen. In one of the electrodes, hydrogen is produced, and on the other electrode, oxygen is produced. Since both the reactions are occurring simultaneously, as hydrogen will be produced, similarly, oxygen will also be produced. Yes.
And also we can produce the carbohydrate also we can produce.
Yes, that was I discussed about two types of artificial photosynthesis. One was carbon dioxide reduction to hydrocarbons, and the other was water splitting. In the first approach, that is carbon dioxide reduction to hydrocarbons, you can produce glucose and other hydrocarbons. But as I said, it is not commercial and it is not pursued because that is energetically more consuming process, we can say. The activation energy required is very high, and we don't have efficient devices that can be used to reduce CO2 simultaneously. That's why we are mainly focusing on water splitting, but yes, that is also being pursued.
Will it be more than efficient for natural artificial photosynthesis?
uh,
Natural photosynthesis?
Okay, so no one can deny the importance of having plants. Of course, we cannot produce that much oxygen to fuel all of us, all the living beings, and we definitely require plants. But yes, we can produce oxygen and we can produce glucose. But in the lab scale, I don't think that much glucose will be produced that can fuel everybody.
Thank you.
Yeah.
Yeah, maybe we can say that as of now, we cannot produce or replicate whatever happens in plants in lab, but we should not also be hopeless about the future. Okay, anybody else has any question? If you are hesitant to ask, maybe you can type it in the chat box. Okay, so I guess no one is going to ask any further questions. We will meet again soon, and I hope it is in person this time. So maybe we can take a leave now. So goodbye, everyone.
Thank you, everyone. Thank you for your time. Bye bye.